So today I'm going to talk about laboratory IR spectroscopy of protonated fullerenes. Fullerenes might need to be introduced because, oh, now it's not working. Wait a minute. Okay, now it's working. Yeah. So fullerenes is one of our most iconic molecules. They are very special. They've been studied in many different fields. What we can see and we can say in this like astrochemistry matter that they are very stable and they can survive under intense radiation in a very harsh environment. And that makes them a very good candidates to be present in space. And actually, these molecules like C60 and C70 are the largest molecules found in first in a planetary nebula, then later on in different parts of the interstellar medium. Not only the neutral fullerenes, C60 and C70 are interesting, but also other derivatives of this molecule can be present in space. One of the candidates is protonated fullerenes. These molecules have a very high proton affinity, maybe not very, very high, but like we can compare it to ammonia, which is a good number. And that makes them likely to be formed when we have like neutral fullerenes. So in part when we have neutral fullerenes as well. What makes them special, like if we compare to like, for example, hydrogenated fullerenes or other derivatives of fullerenes, that adding one proton to this carbon cage will so with this, the aromacity will stay and the stability of the molecules will remain the same. So it won't be destroyed in the interstellar medium. We won't see like cage opening like what we would see with hydrogenated fullerenes. And actually, in earlier studies, it's been stated by Sir Harry Kroto that protonated C60 is likely to be the most abundant fullerene analog. C60 and C70 are both highly symmetrical molecules. C60 belongs to the icosahedral symmetry group, and that means that their IR spectrum, its IR spectrum is very sparse. We find only 4 modes. If you take a look to the C70, it's a little bit more lines, but still a very empty IR spectrum, what we can see. However, if we add something to the carbon cage and we break all the symmetries, then we'll expect we expect new peaks to appear. And if we measure the protonated C60, this is exactly what we see. So on the top figure, it's still the neutral C60 spectrum. And on the bottom one, you can see the protonated C60. And it's immediately very obvious that it's a very, very different spectrum. It's a very rich spectrum compared to the neutral one. And it's all because of this one additional proton. In that case, all carbon atoms identical. It means that we have only one isomer, so we don't really have to think that what can be the structure of this molecule. However, if we go further to C70, that's a little bit more tricky, since we have 5 different carbon atoms. So we have 5 different configurations for protonated C70. And we would like to know that when we measure our spectrum, then what type of isomer we are measuring. For that, a good technique to use is the DFT calculations, so like having some computation on this molecule. But of course, we cannot be really sure that what is the good like basis set and function for these molecules. So first, we use the C60H+, so the protonated C60 spectrum, to benchmark our calculations. We did a couple of different function and basis set calculation on this on the protonated C60, and we could conclude that for this big of a molecule, we should use I could say the usual B-tree-lip function with a relatively large basis set. So later on, we will use this function and basis set to find out the right isomers. What you can see here is the experimental setup, what we used. This is a, so here you can see the ion source, then the mass spectrometer, which is coupled to the laser light to do IRMPD spectroscopy. To produce the ions, it's not so obvious how to do it, since fullerenes are not that easy to get into solution and to ionize it. For making these protonated ions, we used an atmospheric pressure chemical ionization source, which has a corona discharge for ionizing our molecules, and it has the possibility to actually measure solid samples. So we could just directly insert this powder, and we don't have to like use any kind of solution. We used it on different large pHs. That's right now it's under review to publish it, and it's actually a surprisingly good result that really easy to make ions with that. I would like to mention the IRMDP process, what we talked earlier, and I think everyone is familiar with it now. So in the mass spec, so this is like so this is like a mass spectrum we can like usually see with protonated fullerenes. The middle one is the protonated C70, and we can also see the radical cation of the C70. We isolate in the mass spec the peak what we would like to measure. In that case, is the protonated C70, and if we irradiate it with tunable laser light with the right frequency, we will see some dissociation. That will cause a very good quality spectrum, since we cannot break the carbon cage. So we will see fragmentation, but only in one dissociation channel. So we will see only one hydrogen loss, I mean proton loss in the spectrum. We compared our experimental result with previously measured spectrum. So in the middle, it's the protonated C70, which is compared to the neutral C70. And it's, you can see it like right away that it's a very different spectrum. So we will see new peak appears in that region, so between 6 and 9 micrometer. It's very similar to this protonated C60. So we have the strong peaks in that region and a little bit smaller peaks in the longer wavelength region. These peaks belong to like ring deformation and breathing modes. And this part is from CC stretching with hydrogen bending characteristics. And we get to the point to actually see the calculations. So we try to like figure out the right isomer for this protonated C70. And we concluded that the lowest energy configuration, which is the D isomer, is the best matching calculation. So here, the blue represent the calculated spectrum, and the black one is the experimental spectrum. And it's actually a very nicely matching calculation. We also did some comparison with some emission spectra from planetary nebula. And so in this planetary nebula, we know that it's a very Fullerene-rich environment. And as you can see on the spectrum, the black one is the observed data. You can see that the dashed line, which indicates the C60 and the C70 species here. And what we can tell, like that we cannot really assign like peaks, like we cannot really explain the spectrum only with protonated C70, for example, but it's also not possible to do it with just neutral C70. So our conclusion is that like a mixture of fullerenes might contribute to this spectrum. So we propose that it can be from different fullerenes in different ionization form, and yeah, and also like neutral fullerenes together, which cause this plateau in the spectrum. Maybe, we don't know. So as a conclusion, or as a summary, I showed you the first IR spectrum of gas phase protonated C60 and C70, and the computational work on these molecules. And we also had some comparison with spectra from planetary nebula. And I would like to thank my supervisors and the Felix staff and you for listening.